I think that I would introduce you, Jeff, as a scientist, and I hesitate to say philosopher. I prefer to say a student of philosophy, even though I've been teaching it for many, many years. Philosopher always seemed like one of those words like artist. You know, I always preferred it when a painter said, I'm a painter, not an artist, because an artist sort of is a self-congratulatory term, you know, like it's for others to determine what's art, and it's for others to determine whether he's a real philosopher. So I'll just say I'm a student of philosophy, but by bringing a student of philosophy and a student of science together to begin with, it seems to me that we can have a good dialogue about all of this.
And in doing this, I thought a reasonable way to approach this was I put together that I'm going to share on the screen a series of, I guess you'd call them memes. They're not necessarily textbook-like, but they're very brief little scenarios that will hopefully spark discussion. So saying that, I'm going to...
Are you going to bring up the Bruno illustration? Is that what you're going to bring up?
I am
yes,
indeed.
There it is. There it is. Okay, good.
And I thought this would be a good place to start.
All right.
Giordano Bruno did this woodcut that has since been colorized into a picture. It was done in the 18th century and actually appeared in a medical textbook as a front piece. But I think it captures the dilemma of the scientist and the philosopher in terms of materialism. You see on the left-hand side, the materialistic universe with the sun and the tree and the stars. And the individual is attempting to poke his way through the materialistic universe to see the, I guess you'd call it the more spiritual side of things, the things that are behind the veil of the materialistic world that we would call spirituality or religion or God. But I think this captures the dilemma in terms of most modern day people are very familiar with science, they're very familiar with religion, but it's difficult to bring the two together in some ways that's reasonable and not a schizophrenic lifestyle.
And what I like about the drawing, in terms of certain points that I want to illustrate and talk about, is that it shows an attempt to escape from the material universe. The character in the drawing, in the illustration, is trying to escape from the material world. I think one of our first topics has to be, is healing the dualism between mind and matter, between spirit and matter, is healing this split that has characterized our culture for such a long time. Is it a matter of escaping the material world, or is it a matter of reconceptualizing the material world? Let me put it right up front. It seems to me that all your stress about how the real meaning of modern science is that reality is spiritual is itself an attempt to overcome the duality, not by escaping from the material world, but by finding the spiritual in the material world. All your emphasis on field theory, all your emphasis on what I would call communicative nature of all things, right down to the basis of reality, that those little particles in quantum theory that communicate with one another apparently from a great distance. All this stress is really a stress on the fact that the healing of the split is to see the spiritual as an aspect of the material, not as a separate reality that we must escape to from the material. What would you say to that?
I would think you've hit on it here, but I would kind of rephrase it. In the sharing I'm doing here, I call this Bruno's barrier, that seems today to be almost impenetrable, because I guess we owe this to our Greek heritage. We tend to think in binary. It's either one way or the other way, and they tend to be mutually exclusive. And one way needs to be correct, which means the other way is false. And as a scientist, what I'm going to propose here is, rather than to try and develop a compromise between what appears to be two mutually exclusive areas of science and religion, I will be seeking to find a third alternative that's not a compromise, but as a reformulation that uses the most important parts in both areas to reach a new way of thinking. In following what you're getting at here, I think it's important to see where science came from.
Okay.
Because most people attribute it to Galileo, who made the first telescope and started to do the first observational experiments to find out what was quote unquote true with a capital T. But the scientific method actually comes from Sir Francis Bacon, who was apparently not a very likable guy. He was kind of ornery and everything, but he actually was the one who developed the scientific method, and he's credited with formulating. We get our ideas from induction. We then do experiments on these ideas. We then interpret the data, and we then base our conclusion on interpretation of data from experiments. He strongly opposed deduction from authority, which means a scientist or authority with a great reputation says something, so it must therefore be true. He was a big
or the church says something. Let's not forget when this is, when modern thought was emancipating itself from the control of the church. His opposition to authority very often meant the authority of church figures, of the ecclesiastical or religious point of view.
What's sadly become forgotten in the current day, and as someone who's been kind of living in their house for the past year and a half due to COVID and watching way too much TV news, it seems like all of our orientation today is we have to find two people that diametrically oppose each other, let them sit there and argue, and then someone has to be right. The analysis of data in terms of trying to find something that works for everyone seems to have gotten lost, because we have to remember both science and spirituality have the same ultimate goal. The goal is to discover truth with a capital T about our world and about ourselves. And that seems to have gotten lost in modern day.
Yes, yes. Go back to Bacon. What would be your commentary on Bacon?
Someone who was looking for a method that could be reliable in terms of at least finding what is actually so, rather than someone's just great idea that it must be this way because I say it is.
Mm-hmm. So do you see, but how do you evaluate Bacon's principles here, the induction, experimentation, and interpretation of data? Do you accept these as being of the essence of science?
Yes, and I've put together here, for those who don't know, how science actually worked, because most people, when they think of science, think of the data and the conclusions that science reaches, rather than the fact that science is a process. And it's in two steps. Inductive reasoning is used to develop ideas in a theory or hypothesis, and that deductive reasoning is used to test that hypothesis and try and disprove it. And I have kind of an example here of the inductive approach for getting ideas. Someone makes an observation: elephants depend on water to exist. So then we expand that observation to try and see if there's a pattern. Do all observed animals depend on water to exist? And from those two observations and their development, we come up with a theory that all biological life depends on water to exist. Now, this theory, at this point, we have no idea whether it's true or not. It's a good idea based on observation, but a conclusion drawn on the basis of an inductive method can never be proven. It can only be invalidated by observation and experiment. So once you have an idea, you go to the deductive research approach. And for those that are not quite familiar with deductive reasoning starts with premises to draw a conclusion based on logic. All dogs have fleas. That's a premise. Beano is a dog. That's a premise. So the logical conclusion from deductive reasoning is Beano has fleas. The way of attacking or the weakness in any deductive reasoning is the truth of the premises that you used. Based on these two premises, the conclusion must be logically true. However, if one of these premises is not true or false, the conclusion that Beano has fleas cannot be relied upon. So this is bare bones deductive reasoning. In science, we modify that somewhat. When you're conducting deductive research, you always start with a theory, which is the result of an inductive research or ideas. And reasoning deductively means that we now must test what comes out of inductive reasoning. So we start here with an existing theory. All biological life depends on water to exist. You formulate a hypothesis. All land mammals depend on water to exist. Now, if you'll notice, there was a narrowing there from the stated theory to the hypothesis. It narrowed from all life down to land mammals. Why did they do that? Because in order to conduct an experiment, you must limit all of your data to something that is possible to actually generate. To try and test all biological life to see if it depends on water is a task that will never come to a conclusion, but you can get a firmly good grip on land mammals. So they narrow down their test criteria and they then collect data. They study land mammals species to see if they all depend on water. After you analyze your data, you come up with all the land mammals that we did indeed investigate depend on water. Therefore, it supports the hypothesis. The very important thing here is that science can only disprove a hypothesis. It can never, ever prove something conclusively true because you are always just one experiment away of finding a refutation to that hypothesis. And I was really impressed when I was a mentor to a high school student and helped her with her science fair project. The first thing in the handout they gave to her said, do not ever use the phrase, I have conclusively proven that, because no scientific method can conclusively prove anything. But it seems after people get out of high school, they tend to forget that. And I don't know how many scientists you can see on TV that will say, it's been conclusively proven that so-and-so. Totally incorrect. Science can never prove anything conclusively true.
Yeah, that's true if you're talking about certainty, but it seems to me, let's take an example of this. When people wonder whether there might be life in distant places, outside of our own solar system, for example. You know, these new exoplanets that they've discovered, planets that go around other stars, they usually do depend on the hypothesis that if there's going to be life there, there has to be liquid water. They always say that in the articles that you read. So they're always looking for planets that have liquid water. Surely it is true that the hypothesis that life depends upon water, not just water, but they actually say it has to be in liquid state of water in order to generate life. This is how I understand it anyway. In a case like that, surely it is good science to say that it's not that it's been conclusively proved, Not that it's impossible that we could find living things, but nonetheless, it is a strong finding. Don't we have strong findings in science? That is to say, findings in science that have withstood many, many different attempts to disprove them. And all of the testing that has been done has resulted in, we have not yet refuted this theory. So Einstein's theory of relativity is not conclusively proven, but can't we say that it is good science in the sense that it's the best theory to date until such time as it should be changed? And if it ever were changed, this is an additional point, it wouldn't be changed in the sense that it would be refuted. It would be in the sense that it was shown to be part of a larger reality. So that, or to shift to Newton, you use the example of Newton in many of your writings. We did see that Newton was revised by later theory, that Einstein revises Newton, but Einstein doesn't exactly refute Newton. He shows that the Newtonian principles work in a more restricted domain. If you're studying the planets as they go around the sun, then using Newtonian principles, the Newtonian principles of mechanics and the principle of gravitation is a very good approach. But on another level, we now know it's only an approximation that works for a certain restricted group of cases. Newton is still good science in that sense. Is that not so?
Yeah, we'll expand on this a little bit later. What you're getting at here, I think, is exemplified by the American legal system, which is a system that when you have a trial, you need to come up with a conclusion. And so the American legal system has two standards of proof for what is truth. At a criminal trial, the conclusion of the jury must be beyond a reasonable doubt, which is somewhat open to interpretation, but basically you're talking there about certainty. And this is something that it is not possible for the scientific method to achieve. It may work for a jury in a trial looking at certain things, but there is no such thing, as you were saying, as absolute certainty. A civil trial, however, the conclusion of the jury must be that there is a preponderance of the evidence to prove the case. And this is exactly what you're describing here. When someone says there's a successful scientific theory, evolution, for example, it has survived the test of the preponderance of the evidence. We have not really found an experiment yet that someone has done that disproves that. So most of the things that you read in textbooks as scientific information are from theories that have been tested repeatedly. They've been found to be true, or if there's some discrepancy, it's been modified, so that science works on the preponderance of the evidence. And I think that's important to keep in mind whenever you're looking at any type of scientific information. It does not carry the weight of verified fact. It is the preponderance of the evidence of the experiments to date. And there needs to be in the back of your head that tiny little voice that says, but it is not conclusively true.
All right, now why is this distinction so important? Why is this distinction, when we get into questions of mind and matter and the nature of the universe, why is it important to keep this distinction in front of our mind?
Because we have to realize science is a system of investigation. It is not the material that science has developed. As a system of investigation, science has proven remarkably useful over the past 150 years. It is a very good way of investigating any number of things, but you have to keep in mind that it's not like the conclusions of a successful scientific theory have dropped from God and it's truth with a capital T. It's the best we know at any given point. And one of the attacks on science has always been, well, you keep changing. You can't make up your mind. it's always being changed as we go forward. Indeed, it is. That is the basis of how science works. And it's kind of like your road in life. You're on a journey to find something, doesn't necessarily guarantee you'll reach the goal at the end of the road.
Yeah, but let me break in here with by using an example. You use the example of evolution. It seems to me that there's some very fine distinctions here that we have to keep in mind, because I want to say in some sense that evolutionary theory is good science. I don't want to say it's absolutely certain, but I do want to say, when I'm confronted with people who deny evolution, to make the case quite real, because there are millions of people in this world who, for what they think are proper religious reasons, and perhaps for other reasons as well, who actually deny evolutionary theory, actually deny the fact that animals and plants have evolved from certain kinds of more primitive states up a kind of evolutionary ladder to more and more complex forms of being that we can describe. Now, when I'm confronted with an anti-evolutionist, I can't claim that evolutionism is certain. This is something I'm taking away from what you just said. But at the same time, can't we say, as you just said, that it is the best science that we have to date? Isn't there some basis for our being able to rule out anti-evolutionist views as they stand right now?
Well, I picked this because evolution, as stated by Darwin, has evolved dramatically over the past 150 years.
Right, but if you read Darwin, you find a remarkably open man who left a lot of problems unsolved, who said there are a lot of problems unsolved. As a matter of fact, the principles of variation, later on, mutation became very important, but he wasn't very clear what it was that natural selection acted upon. He said that there were great questions left to be found out when it came to the descent of human beings, for example. He wrote a book about human evolution in particular. He leaves a lot of questions unanswered. He's a good scientist in the sense he says there's so much that we do not know. So I want to say the same thing, but at the same time, I want to say that the general approach that Darwin gave us, nonetheless, in the spirit in which he offered it, is the best scientific approach that we have to date. Would you agree with that?
Yes. And I picked evolution for that exact reason. Darwin was not only a good scientist, he was a self-critical scientist.
Exactly.
You read The Origin of Species, he makes numerous statements, and basically we're looking at Darwin formulating ideas in the inductive reasoning part of this. He traveled the world and observed animals. But in Origin of Species, he makes numerous statements that I think this is the way it works, but if this is found to be true, my theory is not correct.
Right.
And what has happened is we have found that Darwin's theory doesn't fit too well now that we have genetic analysis. When DNA was discovered and we now knew the cause of speciation and where the information came from, this basically overruled Darwin and proved him incorrect with what he said. But this has now been formulated into neo-Darwinism, which is the new Darwinism,
right,
which relies heavily on genetics.
Which does accept the basic claim that living forms have evolved from more primitive states, but actually questions Darwin's idea of what the exact process was that produced that evolution. And he was puzzled about those things. But nonetheless, I keep having this anti-evolutionist in mind. The person who actually says we shouldn't teach evolution in the schools because it's bad science or it's unproven science. Well, again, it's not proven to a certainty, but I want to be able to say, look, if we teach science at all, we've got to be able to teach the best science that we have. And the best science that we have does sustain Darwin's broad approach to the matter, even if it doesn't quite jibe with some of his individual propositions about how the process worked in detail. Would you accept that?
It's now worth looking at when you're looking at the scientific method, and particularly scientific materialism, which is the current most populous worldview of materialism. You have to understand its weaknesses. Scientific materialism is a good method, but most people are not aware that it is based on 5 assumptions. And you need these 5 assumptions to bootstrap the creation of core ideas. You can't just pull things out of the air. There are things that are very difficult to test that you have to assume are true in order to bootstrap inductive reasoning to come up with ideas. And scientific materialism is solely derived from 5 basic assumptions about reality that are very difficult to test. They are subject to falsification by experiment, but the experiments are very difficult to construct. But not many people realize that these 5 assumptions are taken on faith. These are assumptions or scientific faith statements that are not set. They are a set of dogmatic faith statements that we are going to assume are true and then move on from there. If these 5 assumptions are not correct, it will change the whole worldview of scientific materialism. So I put together the 5 of them here. The first one is objectivism. This assumption states that the only reality of significance, in other words, the things that we measure and test, exist out there beyond human subjective minds. In other words, I'm investigating the world outside of me and my mind, and I'm going to assume that that world is the real world and it's separate from my mind. That's a basic assumption of the scientific method. What it means is my mind can't alter the data in an experiment. The data exists in the world, and I'm simply looking at the world, making observation and making tests, and my mind has no input into how something is going to come out. The second is metaphysical realism. The assumption that this universe out there can be known by investigating by the subjective mind. In other words, the universe is out there and it exists independent of me, and I can test it without becoming part of the system. The third one is a really important one. It's called the closure principle. This, the assumption which denies the possibility that anything other than material influences can affect any aspect of the natural world. This is the assumption that's always used to minimize or attack religion and spirituality as being impossible and absurd. However, not many people realize that the closure principle is an assumption. It's not tested fact. Just briefly, to just give an example, the closure principle is under scrutiny because of something that's so pervasive in scientific life that most people try not to think about it. The placebo effect. And this is relevant since we're living in the age of COVID, where people are testing drugs and vaccines. Every single clinical trial is done double blind. What that means is the people that are giving the vaccines and talking to the people that are in the trial do not know themselves whether the individual is getting a placebo or the real vaccine. This is to limit any subliminal messages someone might pass to the subject of they're getting the real vaccine versus a placebo. In every single clinical trial, the placebo effect has to be taken into effect because it can constitute anywhere from 1% up to as high as 10% of the results. In other words, what the placebo effect means, but no one really wants to say out loud, is that these people that are getting placebos, through their belief in the drug or the vaccine, are able to have their bodies express what the drug actually does. And this is remarkable, since these people have no idea how the drug is working or anything. But there's a large percentage of people that get a placebo that manifest all of the effects of the drug. And this is a factor in every single clinical trial. So somewhere the subject's mind is influencing their body in manifesting the effects of the drug. So that's just a quick explanation, a real world example. The last two, universalism. It declares that all the laws and the rules that science come up with are universal in that they are the same in every location and at every time for the universe. That's pretty hard to wrap your mind around, but there is a very interesting result that's happening now when by these constants, these laws or rules, there are certain constants that are derived from science mathematically, like the Planck constant and the gravitational constant. They have now honed the measurement of the gravitational constant to a very, very precise number that can be measured. What they're finding is the gravitational constant is not constant. It changes over time and in different places, very minutely, but it's above the level of statistical significance. So this means one of our assumptions that things are constant throughout the entire universe and through all time may not be necessarily true. The last one is a lot of what people are familiar with science, which is physical reductionism. This means that I can reduce everything to a smaller or more fundamental component. And in another session that we'll discuss, we'll look at this. But this is basically saying you can break down the world in smaller and smaller pieces until you get to the basic components. And for modern physics, that is the component of, let's say, an electron. An electron is a fundamental component of an atom, but it doesn't appear to be quote unquote real. If you ask a physicist for a definition of an electron, they will be hard pressed to give it to you, because the electron doesn't appear to be anything real in terms of a particle like a little marble that sits there and exists. It, as we'll see later, when you get down to the very small level, that level doesn't seem to even have any remote connection to the larger material world we're familiar with. Okay.
Yeah, I had put myself on mute to let you speak. Pardon me. I was going to say it's that last premise, the one of physical reductionism, that interests me the most. I'm not sure about I'm not sure that there's as big a problem with the third assumption. If you scroll down, if you'll scroll down back so we can see assumption, the closure principle. I'm not so sure that as we approach things, you and I, that is the biggest problem. It seems to me that number 5 is the biggest problem. I don't have. Let's go. Let me just put in a philosophical remark here. There are different ways in which one could try to vindicate the reality of the spiritual. One is to say that there is a reality beyond the physical. There's another approach that says, no, what the reality of the spiritual is the fact that the material universe is itself capable of what we call spiritual things, events, happenings. and it happens all the time. So that, for example, I'll name names at this particular point. I think that Aristotle, in ancient times, in criticizing Plato, criticized Plato because Plato did postulate a reality outside the physical reality of this world. Aristotle did not deny the spiritual, but what he denied was the physical reductionism of number five. He said the physical world is all there is. If he does say that, by the way, it denies the closure principle here. Did I get that backwards? Aristotle actually does affirm the closure principle, that there's nothing other than physical reality. But what he denies is that the spiritual can be reduced to just the atomistic components of things. He believed, and this is to bring out of the background something into the open that I think is very important. He believed that when you organize matter in more and more complex ways, you get higher and higher forms of intelligence. And intelligence is what is another word, I would think so anyway, the idea that intelligence is a fundamental aspect of the universe, and that different levels of intelligence are attained in the evolution of things in the universe. This is the proper way to attack the narrowness of some aspects of modern science, in thinking that there is nothing but, that we are nothing but the constituents that make us up, and that you can reduce the human level to the level of atoms in the void and so forth.
I think you're right. And that's one of the weakness of some of these assumptions is they're vague. And that's intentional because you can't get more specific. You'll notice in number 3, material influences is in quote. What's a material influence? It's not terribly well defined.
That's correct.
But even more interesting, the early physicists that came up with quantum theory, I've got a quote here by Max Planck. Science cannot solve the ultimate mystery of nature. And that is because in the last analysis, we ourselves are part of the mystery that we are trying to solve. These early physicists all realized that we're not measuring a closed system with us on the outside. We are part of the system. Our mind is part of the system. The experiment that we decide to do is part of the system. You can't exclude the person doing the system from the world out there. You're part of that system. Therefore, you have to be able to account for the fact that we are.
Mm-hmm.
And that's something that all of the early quantum physicists understood. If you happen to read their writings of Schrodinger, Heisenberg, Bohr, they sound like Eastern mystics when they're talking about science and quantum mechanics. And this kind of freaked a lot of people out. It certainly freaked out Niels Bohr, who did not want to consider these aspects. The Copenhagen interpretation of quantum mechanics says the numbers and the equations work. Crank the numbers. Don't even attempt to see how this theory traces back to physical reality. It's irrelevant.
And one might point out at this juncture that that's what bothered Einstein and others. Yes. Was the idea that you could just take these facts, even though they raised all sorts of mysteries and puzzles, you would just crank out the results and don't worry about the fact that you can't make any sense out of it. For an Einstein, you had to make sense out of it. In that sense, you might say Einstein was almost like a religious person who believed that there is an understandable intelligence. And if things don't make sense, if you have contradictions, like ultimate reality is particles, ultimate reality is waves, But how can it be both? Because we originally thought that particles and waves are exactly opposite things. Planck comes in, Bohr comes in and says, don't worry about the contradiction, just grind out your results and teach your graduate students not to worry about it. So by and by, the graduate students got very good at ignoring the fundamental problems. With each passing generation, they were just brought up with this: accept these principles, crank out the results, and don't worry about the fact that ultimately these contradictions don't make any sense, that we can't figure things out at all. So I take it that you're saying that we must, as a matter of fact, raise these questions that have long lain hidden from the time of Bohr, because after all, it wasn't just Bohr who had this interpretation that said, don't worry about the contradictions. That attitude of Bohr's, what you call the Copenhagen interpretation of quantum theory, actually became the predominant theory and still is in a position of predominance today. Is that not true? Is that not true?
Not, yes, it's still taught and it still has its adherents, but it wasn't just Einstein. It was also Schrodinger and Heisenberg. They, especially after Einstein went to Princeton, and he brought up a group of graduate students that were looking at, if science is not telling us about how the world actually works, if we can't relate the ideas that are in quantum theory and reconcile them to how the world works, then the science is useless. It might crank out a lot of numbers. It gives you a lot of technology you can use, but at a philosophical level, it is sterile. It does not help. It does not help the philosophical perspective of, are we learning how the world actually works and what our place in it is.
Okay, and I take it that you believe that there are ways of overcoming the apparent contradictions that we've been talking about, that there's a way of understanding things, you call it quantum field theory, that actually, if taken seriously, does away with a lot of the contradictions and does result in something that an Einstein would be much happier, and Schrodinger and Heisenberg would be much happier with.
Totally, and this, it has been slowly evolving, especially since about 1980 or so. A number of experiments have been done that actually prove that Einstein was correct in his opposition to the Copenhagen interpretation. One of the mind experiments that he did, and I've now totally drawn a blank on it. The
Einstein-Podolsky-Rosen.
Correct. Paradox.
It's a thought experiment.
It is.
It's a reductio ad absurdum, an attempt at a reductio ad absurdum of quantum theory, because it says that if quantum theory were true, then two very distant events would be instantaneously linked to one another.
Right, and that was first proven with an experiment in 1990 and has now been subsequently thoroughly investigated, and we'll talk about that at a later time.
Just to clarify, though, what has been proven now is Einstein was very, very smart. Well, that's a stupid thing to say, isn't it? But he was very, very smart about one particular thing, that quantum theory did imply this result. What you just said is that it has been proven that this action at a distance, instantaneous action at a distance, although those words have to be challenged perhaps or clarified, that this instantaneous correlation between very distant events actually is true.
Well, I think Einstein has been done a great disservice over time, because your comment, everyone thinks that Einstein was a genius. If you read his biography, he couldn't do math worth a crap. In order to come up with relativity, he had to have a tutor come in and teach him tensor calculus, which he had an enormous problem with. So as a mathematical genius, he wasn't. Einstein's greatest ability was he was inventive and a master of inductive reasoning. He was, his power was he came up with things that were so out of the box, no one else had thought of them. Relativity is an absolutely brilliant synthesis of inductive reasoning that is very difficult to draw from just looking at the world. It's Einstein's creativity and his ability to try and link that with the mathematics. But in terms of our standard idea of a genius, he wasn't.
Well, I don't know whether I could agree with all of what you just said. It is true that Einstein had to bring in other people to help him with this theory. I think it was David Hilbert, as a matter of fact, who was the mathematician that he had to bring in when he was working on general relativity, because the mathematics was very challenging to him. I don't have any problem with that, because Einstein was very clear about that. But I do think he was a genius. I wouldn't withhold that term from him. He was a genius because he was able to jump to conclusions and think, as you say, outside the box, and say, let's start all over again with different assumptions. That, it seems to me, that that's the keynote to genius itself, is what we sometimes call thinking outside the box. It's a cliche now that you got to think outside the box, but very few of us actually do think outside the box. And I think it's the earmark of genius to be able to say, let's jump out of the box and start fresh with different basic assumptions. Maybe we can make sense of things that way. So I would not withhold the title genius to Einstein for precisely that reason.
Well, one of his problems in early life was he had zero respect for the public school system. He was almost all self-taught. He wouldn't go to class. He wouldn't take tests. And as a result, he was kicked out of several technical schools and universities because he wouldn't play the game. When Einstein got to Princeton, he totally basically flipped the finger at how college testing worked. Einstein never, ever gave a test. He would evaluate students by sitting down with them at the end of the semester and having a 1-hour discussion with them. And he then would judge whether or not they got anything out of the class. Never gave a test in his life.
That brings us into very interesting questions about pedagogy and the teaching of science itself. It's one of my and in the future, I think we could devote some time to the question, very much alive today, of how good is science teaching in our schools when we're actually taught. Well, let me just say a word or two about this. When you study biology or chemistry or physics in high school, for example, you're presented with a finished body of fact. Learn these facts. So, and perhaps that is something that you have to do to begin with students, is have to get them into things, is to give them the latest results of science. But that's all they are. It seems to me that one of the big problems with the teaching of science is that we don't take a sufficiently historical view of things, that science is always changing. This is consistent with what you want to claim. Science is continually revising itself in view of new findings. You come up with a new theory that deals with a certain range of data, but then you examine that theory. It runs into problems, and you have to produce a new theory that can encompass the old theory, but go beyond the old theory to handle the new data. But that new theory itself is subject to further revision, and science itself is an ongoing enterprise. It is true, isn't it, that some scientists actually believed around the turn of the 20th century, just at the beginning of the 20th century, that science was almost complete. We just have a few more things to do, and then we'll understand the basis of reality. I think it's fair to say that most scientists in their philosophical moments don't hold to that idea any longer, that they see science as an infinitely evolving thing itself. So what we're teaching our students is just science as it stands right now. For example, here's a very, very vivid example in biology, which happens to be your field. When I was a kid in high school, they said there are two basic kingdoms, the animal kingdom and the plant kingdom. If you now look at biology, I'm not going to tell you how many years later because that would date me. But if you would compare the science of my high school days to the science right now, that's no longer the case. They don't just say plants and animals. They've actually rearranged the foundations of things. In my day, but bacteria, because of this idea that there were just two kingdoms, plants and animals, they had to shove bacteria into the plants. There was no place else to put them. But later science has shown that the bacteria belong to a group of organisms of their own kind that are neither animals nor plants, but a third sort of thing. I forget how many different domains there are now, basic domains there are now in science, but it's not just those two. This is an example of how science teaching itself has evolved. They don't teach kids anymore that there are just two kingdoms. They teach them the results of later findings. And these findings now, it would be a great thing if we were to teach our kids how to think scientifically. It would be great to say, as science stands now, this is the way we arrange things. This is the basic taxonomy, means of classification of reality. But I would add to any student taking the course, wait around 30 or 40 years and don't be surprised if there are fundamental reorganizations of things at the foundations of biology.
Well, this is history repeating itself. In the 1890s, Ernst Rutherford, who was quite an accomplished scientist, would tell his graduate students, there's no point getting into science because we only have two basic problems we need to solve, and they'll be solved in the next couple of years. One of them was the black body radiation problem. That's when you heat up something like iron in a forge, it gets hot, it gives off light. They couldn't reconcile the wavelengths of light that were given off by a black body with current theory. The other was the photoelectric effect. The fact that there are materials that when light strikes them, it gives off an electron. Both of these were unsolved problems that Rutherford said, yeah, they'll get cleaned up and everything will be known. It's these two problems that led in the early 1900s to Max Planck basically coming up with quantum theory, which then opened up a whole new world of investigation. I totally agree with you. If you look at the picture on the bottom left, this is what most students think science is. It's a bunch of information in the books, and gosh, the information has to be true because it's science, right? They won't teach me stuff that's not true. I've had the occurrence to be in a high school classroom several times in the past couple of years. There's no investigation, there's no dialogue. It's basically, here's the information, memorize it, spit it out on a test. That's basically how science is taught these days, and it's not doing either the students or the general public any good.
That's why I think, by the way, that one remedy or a partial remedy to the situation would be to change the way we teach science in our schools from this finished body of information approach to an approach that was basically historical, that taught students the history of science. As soon as you see things historically, you understand that science itself is something that is always evolving. And you don't have that attitude that you were speaking of toward these books, that this is the way the world is. Learn it and you'll learn the way the world is. No, what you would learn is that these books are very good books because they summarize some of the findings of science up to this moment. But you would learn to think historically, that just as Galileo was improved upon by Newton, and just as Newton was improved upon by Einstein, and so on into the future, our state of science will no doubt be radically modified in the years to come. If you want to be a scientist, a good one anyway, it's important for you, I'm speaking to an imaginary student, it's important for you to realize that where the great scientists work is in questioning the fundamental assumptions of current science.
Well, this particular thing that's up now goes back to what you were talking about between Newtonian mechanics and quantum theory. And it's a very good example of how science works. Most people are under the false impression that the technology that science has given us through the scientific method, computer chips, semiconductors, any number of things, it is not the same thing as saying this proves that science is true just because we have a lot of technology that was developed from it. In Newtonian mechanics, it's excellent for predicting the ballistics of cannonballs, great for working out pull shots, great for looking at how the planets revolve around the sun. But literally about 115 years ago, quantum mechanics replaced Newton's theory. Newton's theory isn't wrong, it's just limited.
Right.
It doesn't take into effect interactions. For example, the orbit of Mercury was not what you would predict just with Newtonian gravity. It was the effect of the sun through relativity theory curving its orbit. So quantum mechanics then becomes a more accurate way of calculating the same things that Newtonian mechanics do. So we can say quantum mechanics is more accurate than Newtonian mechanics. But here's the important thing as a philosopher. These two theories, quantum mechanics and Newtonian mechanics, describe two very different philosophical realities of the universe. In Newtonian mechanics, basically the world gets wound up and it is now proceeding based on how things interact, and there's no room for human free will or anything like it. It's very depressing. It describes a clockwork universe that has no creativity, no way of accommodating the human mind. So they're two very different philosophical frameworks. And just to give you, we talked about reductionism. So now we get down to what is an electron. We go all the way through molecules, and all molecules are made of atoms, and atoms are made of proton, neutrons, and electron. When we reach the electron, we hit a brick wall. At the bottom here, you see what an electron is. These are all the orbitals of one electron in hydrogen based on Schrodinger's equation. The electron isn't a physical particle at all. It's a realm of possibility. And that's what freaked people out about quantum mechanics, is that we get down to the tiniest levels and the world isn't what we think it should be based on our five senses. It's something very different. And the most current formulation of quantum field theory, which you alluded to a while back, it was actually developed back in about 1970, but it took a long time to develop and catch on because in quantum field theory, there is room for the subjective and the spiritual. In quantum field theories, basically, there is a small heresy involved that particles are not primary. We live in a world of materialism where particles are everything, atoms, molecules. When you get down to it, there's no such thing as a particle.
Let me interrupt for a second, because every time we make a step like this, you feel I feel an urge to define our terms just a little bit. A particle meaning a well-defined entity with well-defined edges. For example, in the Bohr theory of the atom, you have this idea that there's a nucleus. That's the part of the atom that has the proton, protons and neutrons. And in the case of hydrogen, just one proton, but that's the nucleus. And going around that is a little tiny ball that so that in school we learn to visualize the nucleus as a bigger ball, okay, and the electron, because we actually assign a mass to it which is much smaller than the mass of the nucleus, we found that out. We treat that as a little tiny well-defined ball. So it's like a BB going around a larger entity. Okay, but the point here is that we treat all of these things as if they were things, well-defined things, whereas the basic import of your wave or field theory is that actually electrons are smudged out in space. And by the way, I have a question for you. You're the scientist here. If you treat electrons this way, as if they don't have well-defined boundaries, it doesn't it seem to be the case that an individual electron is in some sense all over the universe?
You're absolutely right. You've just quoted the basic statement of quantum field theory. Fields are primary. Particles are derived from fields when you poke it. To give it, basically you poke it. A particle has a defined location and a defined velocity. A field does not. A field is spread out in space. So the biggest thing that makes people uncomfortable with quantum field theory, it has moved particles to a secondary derived function of fields. And the final thing I have here.
Or rather, that particles aren't really what you see when you see a ping. When you see an event at a certain location, you call it a particle. What you're actually seeing is an activation, a large energy event at a certain part of a field, but the field is the whole reality. And don't mistake this one particular area of concentrated event with the whole thing.
Okay, I mean, this is a bit oversimplified. The picture here on the left shows a quantum field, and you see it's distributed and there's values in the field that are different by their height all over the place.
That's right, right.
When you excite a field, you generate a discrete particle, which would be the little blue balloon taking off over on the right-hand side of the picture. Particles are always part of the field. They never really separate from it, yet they get excited, they appear, and then they can disappear. We are horribly biased by our 5 human senses. Our 5 human senses does not get to see or investigate what's actually fundamental in nature, which are fields. We only get to see the excitations of various fields and how they impact our senses. So I thought this was a fairly good place to end. All of this stuff, to tease people to come back, will be explored in greater depth later.